studied in compressible fluid flow that the density of the fluid does not remain constant, but due to the increase and decrease of the density, there may be a formation of a pressure wave, which is also called as a sound wave. So, let us take into consideration that is propagation of sound through a compressible fluid. As we have seen in compressible fluid flow, that the density of that entire fluid changes as the pressure changes. So now what we are going to consider, that is generation of pressure wave or generation of a sound wave. So let us see what is a pressure wave or a sound wave. Now let us see what is a pressure wave. Pressure wave and sound waves are two waves which are interconnected to each other. Now how they are interconnected, let us understand this. Sound waves actually travel in the form of compressions and rarefactions. Now sound wave is actually a longitudinal wave. That means if this is the direction of propagation, the particles will also vibrate in the direction of propagation in a longitudinal wave. So what happens exactly in a longitudinal wave? That the particles are vibrating in a longitudinal direction. So when all the particles come together once, then the density of this entire space or entire fluid changes, because the particles are closely packed to each other when they are vibrating, and at the same time while they are vibrating, all of them come together. So this part of a wave is called as the compression, where the density is very large because it is a closely packed object. So in rarefaction, what happens is these particles move away from each other, so the density of the fluid decreases. So this is only possible in that fluid flow where the effect of pressure will create a compression and rarefaction. It will only be created in a fluid which will be a compressible fluid, which is able to be compressed under pressure. So we have a compression over here, we have a rarefaction over here. Again there will be a compression, and then again we will have a rarefaction. Again in compression the density is going to increase, in rarefaction the density is going to decrease. Now this is actually called as a pressure wave, or it is also called as a sound wave, but there is a difference between a pressure wave or a sound wave. A pressure wave is only a sound wave when it is in an audible frequency. That audible frequency, as we know, that is 20 hertz to 20 kilohertz. This is the audible frequency in which the sound waves we can hear. Rest of that, if the frequency is less than this, then it is a pressure wave, but it is not audible to us. And if the frequency is greater than 20 kilohertz, it is also a pressure wave, but it is not audible to us. But within this range, that is 20 hertz to 20 kilohertz, this is a pressure wave, but which can be heard to us. Hence it is called as a sound wave. So we have seen the basics of a sound wave, which will have compressions and rarefactions. Now next part which we'll see is the velocity of sound in different states of matter. Now, for propagation of any wave, we can see that there is exchange of vibration between the particles. Means the initial particle over here will be set into a vibration. This vibration will be passed on to the other particle when this particle will hit the second particle, and the next particle will also vibrate, so on and so forth. All the particles in the medium will vibrate. Now this is only possible if the particles are very close to each other. if the particles are very away from each other, if they are away from each other, then the rate by which the disturbance is passed from one particle to another particle decreases. That means we can safely say that we have three states of matter. First state of matter is a solid. Now in solid, what happens is all the particles are very close to each other, very close to each other. So let us draw all these particles which are very close to each other. If one particle is set into vibration, then immediately it transfers the vibration or disturbance to the next very much particle. So next very particle, and during this, the vibration in entire length of the solid is transferred at a very effective rate or in a very small amount of time. So this is the reason why velocity of sound in solid is always higher, always higher than in any other medium. Rather, it depends upon the density of the medium. If the density of the medium is very large, that means if it is a closely packed solid, then the then it can transfer the velocity of sound effectively from one particle to another particle. Let us go to the next state of matter, that is liquid. Now in liquid, particles are a bit far away from each other. Now what happens is, if there is some disturbance in the first particle, then it will take some time to travel this intermolecular distance, small amount of intermolecular distance to travel to this other particle. But if this are n number of particles, and if there is a time lag between transferring the disturbance from one particle to another particle, what happens is velocity of the sound decreases in liquid as compared to the velocity of sound in solid. Now, over here, the intermolecular distance are very less, so it can travel quickly. Here, the intermolecular distance are a bit higher, so it takes time to travel from one point to another point. Whereas, if you consider the third state of matter, that is gas. Now, in gases, if we see, the particles are very much away from each other. So to travel a disturbance or a pressure wave from one particle to another, it takes a long amount of time, or it takes a lot of time to travel the distance from one particle to another particle. Hence, velocity of sound in a solid is the highest because it is closely packed, then in liquid, and then in gases. So these all things we take into consideration for propagation of velocity of sound. So now, next thing we'll study, that is the expression of velocity of sound. So let us study what we have seen, the basics of sound. Now let us study what is expression for velocity of sound. So now we have the expression for this. What we'll do is we'll take a cylinder. In this cylinder, we'll attach a piston. Now, to this piston, we'll apply some amount of force in towards right. That force will be converting into pressure since it is uniformly distributed, and this piston will go from its initial state to some final state. So it has traveled a distance of, let us consider from the initial part, the distance is x. So during this, when we apply the small amount of force, there is a generation of pressure wave. Due to the application of this force on this entire piston, there will be some amount of pressure on the fluid which is inside this cylinder. Now, we'll make sure that we are applying a pressure such that it is creating sound. Now, to create a sound, this should oscillate with a frequency of 20 hertz to 20,000 kilohertz in between that. So that pressure wave is said to be as a sound wave. So now we know what is a sound wave, that is generation of sound in this entire cylinder. So now the sound will travel a large amount of distance in the same amount of time. Let the distance be L, that is along the length of the cylinder, and the piston is traveling by a distance of x. So there is a generation of sound. Now let us see if we can develop a expression over here. Now let us define few terms. That is, first term is x. X is distance of piston from initial position. Next expression is L. L is distance of sound from initial position. Distance traveled by the sound from the initial position. The next we will define few terms. First term we will define, that will be the pressure which we apply over here. Let the pressure be P at the initial condition. So let us consider this as 1, this as 2. Now, since we have applied the pressure in the opposite direction at 2 will be P plus dP, since there is addition of pressure, that is increase in a small amount of pressure. And initially the density of the fluid is rho, and due to application of pressure there is change in the density, that is d rho. So we have defined 5 terms. First is the initial pressure, second is the final pressure at 1 and 2. Next is the initial density and final density at both the sections 1 and 2. X is the distance of piston from initial position, and L is the distance of sound from the initial position. Now the important part over here is dt, that is the time. Now what is dt? That is the time interval or time requires for this entire piston to go from position 1 to position 2. In the same time, since the velocity of sound is very large, the sound will travel from initial position to this final position. Let us consider this as 3, and this initial position is 1. So sound will, since it will have a higher velocity, it will travel by a distance of L, and since the pistons will have very low velocity, it will travel a distance of x. The next term which we will define, that is a capital V, that is velocity of piston, and capital C, that is velocity of sound. C is the velocity of sound. So we have defined all these terms. So let us write down all the terms one by one. So first term is a rho, that is density when it is at the initial position. Then density rho plus rho when it is at the final position. The next part is P, that is the initial pressure at the initial position, and P plus dP, that is the pressure at the final position. Now other terms which are over here, which is dt, that is the small amount of time required for the piston to go or travel a distance of x, and capital L is in the same amount of time how much distance the sound will travel. It will be linked with velocity of piston, and this will be linked with velocity of sound. So these are all terms we have to take into consideration. Now We know that this entire flow is an incompressible. It is an compressible fluid flow, and here we'll apply law of conservation of mass. That is, the total amount of mass in the entire system will remain constant. So now let us see and let us apply conservation of mass in this entire system. So according to conservation of mass, initial mass is equals to the final mass, or initial mass at section 1 will be equals to final mass at section 2. So we have two things according to law of conservation of mass. So let us check out what is initial mass according to this entire term. Now we know that density is equals to mass upon volume, and mass will be equals to volume into density. That can be written as area into length into density. So we know all these things about mass. So now the mass at the initial position can be written as, so let us consider mass at initial position as m1. So this can be written as rho into area into length. That is the mass over here. And mass at the final position m2, here mass is a function of density, but at the final position the density changes. So over here this will be rho plus d rho. Area of cross section remains constant, but as we compress this entire fluid, the length of this entire fluid decreases. For example, let us see this. This is the initial length, and since the piston pushes the compressible fluid ahead, the distance over here becomes L minus X. So there is some decrease in length. So now let us substitute this decrease in length in this equation. So that is L minus X. So we have got what is initial mass and what is final mass for this entire part. So now let us substitute this values over here. So this will be equals to rho area into L. L is the distance traveled by sound in that small amount of time. So what is that small amount of time? Let us see over here. That is how they are linked to each other. C is the velocity of sound. L is the length traveled by the sound. So L is equals to C into dt. Well, whereas X is equals to V into dt. So this is distance traveled by piston X in small amount of time dt. This is the length travel or distance traveled by the sound in a small amount of time dt. So now let us substitute this in this equation. So what do we get? This is C into dt, and this will be rho plus d rho into area of cross section into C dt minus value of x over here is V dt. So we have both the difference in the length. So from here we can take dt common, and this entire part rho plus d rho into area into dt will give difference of velocity of sound and velocity of piston. Now we know, as we know from law of conservation of mass, that the mass in the entire system remains constant, and this entire process which we chose over here is a closed process. It can exchange energy with the surrounding, but it cannot exchange the matter or mass with the surrounding. Hence the mass remains constant in both the parts. So we can write over here, according to conservation of mass, m1 is equals to m2. That is, the mass initially will be equals to the mass final. Let us substitute this in this equation. So let us substitute this in this equation. So this will be rho into A into C dt is equals to rho plus d rho into A into dt is equals to C minus V. So now in this equation, according to law of conservation of mass, both will be equal. These two values will go away. Now let us expand this, and also over here area of cross section is same. So what we are left with over here, rho into C, rho plus d rho into C minus V. So these are the values which we have got from this equation. Now over here let us expand this and calculate this value. So this will give us rho into C is equals to, let us write down this entire equation, d rho plus d rho C minus V. So this expansion will give you rho C minus of rho V plus d rho C minus of d rho V rho C. So now after expanding this part, two expressions will go away, rho C and rho C will go away because they both are constant. The next expression what we'll see over here will be left with all these expressions. Now over here the product of d rho and V, we will tend this to 0. Why? Because due to small application of pressure, there is a very small or minute amount of increase in the density of the fluid, and the velocity of the friction in total will be very small. So the product of both of them is also small, so we can take this, it is tending to 0 and it is negligible. So it is negligible. So this part now tends to 0. Now it is negligible. So now what do we get over here? Rho into V is equals to d rho into C, and C will be equals to rho V upon d rho. So now what we have got, expression of sound is product of density, initial density into velocity of piston upon the change in density. So not always there is piston which is actually creating a pressure wave or a sound wave. So we need to substitute what is velocity of piston. So for that we will apply law of conservation of momentum. Let us apply Newton's second law of motion for this entire expression. So let us apply Newton's second law. So now, according to Newton's second law, the force is directly proportional to rate of change of momentum. So for that, we will just draw a diagram for a time being which will depict the forces. Let us draw the forces. So the force will be here as well as on this entire piston. So now there are two forces which are acting over here, that is force which is at the initial part and the force which is at the final part. So now we know this force will be equals to, F is equals to pressure into area. Now why it is pressure into area? We are applying a force towards right, but that is spread over this entire top cylinder of the piston. Now during that it is converting into pressure. So over here the initial pressure can be written as P into area of cross section, but the final pressure is P plus dP into area of cross section. So the change in the force can be written as delta F will be equals to F final minus F initial. So final force minus initial force can be written as P plus dP into area minus P into area. So the change in the force can be written as change in pressure into area. So now this change in force will be given as summation of force, that is final force minus initial force, will be a mass into acceleration. So this can be written as mass into V minus U upon T. So that is final velocity minus initial velocity upon time. So let us substitute the values in this equation. So the mass over here will be equals to rho into area into C into dt. So now how do we come to this point? Well, we know from the initial part where we had considered the mass initial will be equals to rho into A into dt. So that is what is mass of that entire fluid at that moment of time. Now initially the velocity Initially, the velocity is 0, but finally the velocity of the piston is v. So let us substitute this in this equation. So what do we get over here? Summation of fx is equals to m. Let us write down this entire expression, v minus u by t, where m is equals to rho ac into dt. So now let us substitute this. U is equals to 0 because we are pushing the piston. Initially the velocity of the piston is 0. The final velocity of the piston we have already defined that as v, and all these will take in some amount of time. That time is dt. So let us substitute everything in this equation so that summation of force will be equals to rho area C into dt into V minus 0 upon the time required for this entire process is dt. So over here dt and dt will be cancelled and we are left with over here the left hand side of this expression is dp into area, which we have seen earlier, and this will be rho into c, rho into c into area into v. So these things, area and area, will go away, and what we will be left with, that is rho v into c is equals to dp, or c is equals to dp upon rho into v. So now we have got this expression in terms of change in pressure and density, and initially before this we had got an expression of the velocity of sound is rho v into upon d rho. Let us consider this as equation number 1 and this as equation number 2. Let us write down those both equations one after another. So what do we get over here is the initial expression is equals to dp upon rho into v. This is equation number 1. Now currently the equation is rho v upon d is equation number 2. Now if we multiply these two equations, so we get a c square is equals to dp upon rho into v into rho v upon d rho. So rho v and rho v will go away and we'll get velocity of sound is square root of dp by d rho. So that is change in pressure to change in density. Now this formula actually was devised by Newton, and this is called as Newton's formula for velocity of sound. But unfortunately, this does not depict the exact velocity of sound. There was some correction which was suggested by Laplace. So now in this part, Newton assumed that it is an isothermal process. That means during longitudinal compression and longitudinal elongation, that is compression and rarefaction, Newton assumed that during compression, when the particles come together, the density of that entire fluid increases, which is true. But he also assumed that heat is generated when all the particles come together, and when there is rarefaction, these particles will go away and heat is dissipated towards the surrounding again. So heat is generated in compression and heat is lost in rarefaction. During compression and rarefaction, the temperature of that entire fluid remains constant. This means what? Heat loss is equals to heat gain, which will tell us that temperature is remaining constant. So he assumed this process as to be an isothermal process. Hence, over here, this formula is also called as Newton's formula for velocity of sound. Now, what we need to do, we have to assume different types of processes. So, let us assume first process is that is isothermal process. So, velocity of sound in isothermal process. Now, we have written over here that is C is equals to square root of dP by d rho. So this is what we know. And according to isothermal process, that is delta T is equals to 0. That is change in temperature is 0. And we know that P upon rho is equals to constant, or P1 upon rho 1 is equals to P2 upon rho 2. So this is actually what is expression for isothermal process, or we also write this as P1 V1 is equals to P2 V2, but we have to consider density into consideration. So let us take this expression into consideration, and we need the value of dP by d rho. So let us calculate what is dP by d rho. So we know that P upon rho is equals to constant. So we'll take over here differentials. So d into rho raised to minus 1 differential will be equals to 0. So we are trying to calculate what is the change in this entire part. P derivative of rho raised to minus 1 plus rho raised to minus 1 derivative of P is equals to 0. So now let us expand this. So this is P into minus 1 rho raised to minus 2 into d rho plus rho raised to minus 1 into dP is equals to 0. So this we have applied chain rule. This is n x to power n minus 1. So this we have got. Let us divide this entire part by rho raised to minus 1. What do we get over here is minus of P rho raised to minus 1 into dP into d rho plus dP is equals to 0. So let us take this on the right hand side. So this is a dP is equals to minus P rho raised to minus 1, rather this will be plus P into d rho. So over here from this expression we'll get dP by d rho, dP by d rho is equals to P upon rho. So we have got what is change in pressure to change in density. So for an isothermal process, the value of C is equals to square root of dP by d rho, which is equals to square root of P by rho, which is constant. P by rho is equals to constant, and square root of that entire part will be also constant. So this will be for an isothermal process. Similar to this, let us evaluate what is expression for velocity of sound for an isoentropic, for an adiabatic process. Now, for isentropic process or an adiabatic process, delta S is equals to 0, and it is governed by an equation, that is PV raised to gamma is equals to MRT, and we have already proved this earlier, that is P upon rho raised to gamma is equals to RT, which is equals to constant. So, to calculate the velocity of sound for an adiabatic process, what we need, the value of C is equals to square root of dP by d rho. So, we need to calculate this value of dP by d rho. So, we know over here P upon rho is equals to constant. So, P upon rho raised to gamma is equals to constant. Let us take differentials over here. So, now let us take differentials. So this is a differential of P into rho raised to minus gamma is equals to 0, because the change in this part will be 0, because rho into P into rho upon rho raised to gamma is equals to constant. So now this will be P into derivative of rho raised to minus gamma plus rho raised to gamma minus gamma into derivative of P, that is equals to 0. So now let us write down this part. So this will be P into minus gamma rho raised to gamma minus 1 plus rho raised to minus gamma into dP is equals to 0. Now let us divide this entire part. We have missed one term, that is the continuous derivative. So this is the chain rule by which we will get the value of d rho in this part. This will be entirely divided by rho raised to minus gamma. We are just dividing the both equations. So this part and this part will go away. So now what we have got over here, that is minus of P gamma d rho into rho raised to minus 1 plus dP is equals to 0. So now let us take this on the other side. So what we'll get, that is dP is equals to P rho d rho into rho raised to minus gamma. So hence dP by d rho will be equals to gamma P upon rho. So now let us substitute this in the velocity of sound. What do we get over here? That is C is equals to square root of dP by d rho, which is equals to square root of gamma P upon rho, or it is also equals to gamma RT. So this is what is velocity of sound for an adiabatic process, or it is also called as Laplace correction. I hope you have understood what is velocity of sound in adiabatic process, in isothermal process, and deduction of velocity of sound in a compressible fluid flow. Thank you.